this node or this node actually works. Just like before in the simple command, where we had a command creator for a node, we need a node creator, and it's the exact same thing. It just needs to return a pointer to an instance of your node, and you could have called the class anything you want, but it's going to return an instance of our shake node. And the next thing we need is the node initializer, and this gets run once when the entire class is getting set up, when the plugin is being loaded for the first time. So this is where we actually create and set up our attributes. Before they were placeholders, but once the node is actually ready to go, it can actually get its attributes set up properly. Let's make some more room here. Okay. All right, so the first thing we're going to handle is our inputs. And the way we do that is we have to, from the OpenMaya module, get, and you'll notice that these MFNs, these are all function attributes, function modules, classes. And what we get here is we need a numeric attribute creator, and we also need a unit attribute creator, and this is going to be for our time, and this is going to be for all our other numeric attributes. So you get these creators. And then what we do is first we're going to say we need to set up our amplitude on our shake node. So we say from our numeric attribute, create an attribute with a long name called amplitude, a short name called amp. The value type of this attribute is a float. And to explain this format here is from the OpenMaya module, from the numeric data, we need a float. Actually, we could have written this shorter, like that, but I want you to see where these come from, because this is an instance of a numeric attribute, this also has those constants. So let's just put this back, and you can see, oh wait, my mistake, I'm sorry. This is a numeric attribute. This is a numeric data. And this is the class that actually holds the constants, my mistake. So as you saw before, k is constant, 3 float. This is just a constant number that tells it that the type is a three position float. And again, we do the exact same thing for our frequency. Long name frequency, short name FREQ, and then we need a float, and these are defaults. So if you don't specify this, all the values are 1. If you don't specify the attributes for the frequency, all the values are 1. And now we need a seed, and a seed is what we're going to use for our random generator, and it's so that it's only pseudo-random, and if you specify the seed, you can get the same result back every time, because if you produce a result and you're animating to that, or you're keying off that, you need to be able to reproduce that functionality. So the seed lets you control the exact results of the randomization. Each new seed would be a different set of randomization. And before I go any further, I have to explain these parts here. Now, each time we make an attribute, we can set some options on that attribute. And in this case, for the amp, we want it to be able to be storable in the file. So when you save the scene, it can actually write the value of the amps to the file. So when you bring it back out again, it doesn't go to default. It actually sets what you saved it at. And you also are allowed to keyframe it. Same here. We want to write it to a file, and we want to be able to keyframe it. Same here, except we don't want to be able to keyframe the seed, because if you keyframe the seed, it's going to really make your results crazy every frame. So there's no point in keyframing it. So we're just going to disable that. And we're going to say that the minimum value is 0, because we don't need to allow negative numbers. We'll just do anything positive. And now for the octaves. I'll explain what the octaves are in a moment, but in general, they control the smaller and smaller levels of randomization. If you remember in the, let's open up our graph editor. If you look at these, you have the large randomizations, but then as you get closer, you have these smaller. This is not quite a smooth curve, and neither is this. We're adding smaller and smaller jitter, and it makes it a little more realistic if you want to add more and more jitter, but you have control over that. So we say octaves, short name oct. It's a numeric data, and then this time it's an integer. And the default we're going to say is 3 octaves. It can be stored with the file. It's keyable. And we're going to say the minimum is 2, because if you go any lower than that, you're basically just going to have a really smooth curve, we could allow them to go to 1, but I think 2, for our purposes, let's say that's the lowest it can go. And now also now we have to get the time. Now you notice we're going to use the unit attribute from up here. If we're using numerics before, now we're going to use a unit attribute. And we're going to create a current time is the long name, time is the short name. From the unit attributes, it's a time format, which is actually another type of object. So when we get the value of this, we're going to get a time, an mTime object, as opposed to these concrete values like this. We're going to set it to hidden because they don't need to see this value in the node. It's just for our internal use. And it's not going to store it either because it's completely driven by an outside source. And then the last part is our output node. So we set the reference to the output. It's a numeric attribute called output, short name out. Again, it's a numeric data, a 3 float, and the default is 0 so that at a very default value it does not do any kind of movement. And it's not storable, not writable, and it's not hidden because we don't want to store the output of this. We want it to be computed from all these inputs. So even if it gets written to a file, these will still just get generated again to drive this output. Then after we define all of these, we have to actually add them into our shake node. So we use the shake node, and because we inherited from MPX node, we have this add attribute, and we just add all of these attributes into the shake node. It kind of registers them. So we have a handle to them, but it's also registered as part of the node. And the last thing you can do is talk about how you want one attribute to affect another. And this is where we were talking about which node will come in the compute method. So we want to say that every one of these inputs, the amp, the frequency, the seeds, the octaves, and the time, all affect the output. And what this means is the concept of dirty and clean. So if we go back up to our compute, I'm going to jump to the compute method. When a plug, which is a attribute that holds the data on a node, a connectable part, is dirty, it's going to be reevaluated. And in this case, we only care about when the output node is dirty. So let me jump back down. And we want to say that if any of these attributes change, output needs to be recomputed and set to dirty. And then finally, we just have our boilerplate code like you remember in the simple commands. We just initialize the plugin. Here's my name. It's version 1.0, and as I version it up, I can keep saying 2, 3, so that it shows up in the plugin manager. And then we just register it like normal. So again, this is just boilerplate code. And if you see right here, we're using the node ID. And this is that part where it registers it with that node number. All right, so now that we've got the whole setup laid out here, we can go back and talk more about the compute method. All right, so like I said, we only care about computing the output because everything else is driven by either the user setting the input or by that time. So after we get all of our data, and right here, like I said, we get back an mTime from the time attribute, and mTime has a method called asUnits. And asUnits takes a constant of what kind of unit you want back. So mTime has a constant called seconds. So this says, give me back the value of mTime as seconds. It has other attributes, like if you just want to get it in minutes or some other unit of time. But we care about seconds in our case. So now what I'm going to do here is we need to generate new x, y, z points. And I'm calling another method that we have down below called getShake. And getShake is going to take the current seconds value, and it's going to take the frequency x. So you can see here we take, because we have a 3 float, frequency and amp are 3 floats. They're an array. So I can get the x, the y, and the z. Same with the amp, x, y, z. Then we give it our seed that was brought in, and then we pass it the amount of octaves. And now you see what I'm doing here is I'm modifying the seed by a constant amount each time. That's where we get our randomization. As you remember in the, I should really leave this open instead of constantly bringing it up again. As you remember, we have randomization between the three. They don't line up over each other. And this is where we get that functionality, is by adding an arbitrary amount. This could be anything really. It could have been 100. I just chose 250 and 500. If we had not done this and just passed in seed each time, then it would be the exact same, unless of course the frequency and the amps were different. But if the frequency and the amps were all the same, as in, let's see here, select this again. If, in this case where they all are the same, then it would lay right over each other and be the exact same curve. So that's why we randomize these seeds. But again, you would get constant, because the seed itself all comes from the same seed number, this is reproducible. Okay, so once we get our new XYZ values, we need to set, just like we got the input value here, we use our data block to set the output value. We pass in our handle to the output node that was defined up in the class attributes, and we are given back a handle. Now, this gives us just a handle, just like these are just a handle to the input value, although we did cast this right here, so then you get the value. If I had taken this off, like that, then you'd get a handle to it. But we just wanted the value. So down here, we get a handle, and then we set the float 3, x, y, and z. And this needs to match up with the right type. If you tried to set it to something else, you might get an error. You might be able to set it to 2, I'm not really sure, and just pass x, y. But just to be safe, let's make sure it's set float 3. And then the final thing we do on the data block, we set this plug to clean. So if we were able to generate a new value, then we have to make sure to set it clean. And that means that this doesn't have to be computed again until something affects that output node and makes it dirty. Now say we were in here and we were trying to figure some stuff out and we didn't like the current state of data, we could leave it dirty, meaning that it needs to be reevaluated again next time. But this is where you say, okay, I've given it the right values and I set it to clean. And the last thing we do is we return a constant success from OpenMaya. mStatus contains all the status signals for any kind of error. So one of the constants is success. And then what you need to do is if it's not going to check the node, the plug that you want, the default return value needs to be unknown parameter, meaning that there was nothing needing, this plug didn't need to be computed. So if some other output or input attribute came in here and it wasn't one you were operating on and you didn't set it to clean, you should default return unknown parameter. So now's the point where we actually get into what getShake does. And to generate our shake value, before I explain what getShake is let's look up at the top of our node, and you see that I imported this pnoise. And pnoise is Perlin noise. If I open up this Python directory, and the reason that we're able to, well, let me get into that in a second, but let's open the pnoise. And actually, I'll explain. The reason we can actually import it like this is because if you remember, we set our Python path to plugins Python. Now, generally, like I said, you could set this to a facility location or a common location, but for our project, we added this to our Python path, which makes everything in this directory available for direct import. So we import pnoise, and what this is the algorithm designed by Ken Perlin, and this is the actual source of his. He wrote it. His example is in Java, and I took this from this website here, where someone rewrote this in Python, and I just made a couple small tweaks to it. But what he does here is, and you don't have to get into how this works because basically I don't understand it. It's beyond my level of math. But he just starts with this huge table of pre-generated values, and he has these various functions that end up creating what you saw as that noise. It just does a bunch of math, and given the input values, it'll give you back a randomized number. So all we're going to do, again, you don't have to understand how this works because I barely understand it myself. All you have to know is that we are importing it and going to make use of it. So if I come down here to the get shake, this is where we actually generate our random numbers. And as you can see from when I called get shake, it takes a float time, it takes a float frequency, a float amp value, a seed, which we say is a default 0, so if you didn't specify the seed, it'd be 0, and octaves, which is default 3, and it's going to give you back float noise value. All right, so let's look down here and see what we do. So what we do is, we just do a catch, like if they passed in 0 amp, 0 frequency, just return 0 because there's nothing we can really generate. They need to pass in some sort of amp and frequency value. And then we go down here, and we're going to loop over our octaves. And what this does is, if you do range 3, that's going to loop over 1, 2, and 3. And you see I'm using this special syntax again because we actually don't care about the number, the octave number. We just want to loop 3 times, or for whatever amount of octaves they pass in. And what this is this is a fractal sum. And what this does, and again, Ken Perlin defines how to do this on the website at the top of this file. But what we're going to do is every time we loop in an octave, we're going to generate noise. And we're going to do it multiple times, but every time we loop, we're going to increase the frequency by, we're going to double the frequency, and we're going to have the amplitude. And then we're going to add the results to the value. So let me show you what that does. Okay, so as I said, you have this really fine functionality here. So if I were to do it again, let's see here, let me create a new scene, move this down, and let's create a new sphere here. Okay, let's set the octaves to something crazy like 8. Okay, and let's bake those results. I'm just going to bake it to like 300 so we can go quicker. And let's just so you can see some differences. Let's make the Y bigger in amplitude, and then let's create the frequency. Let's say this only has half the frequency, and this has double. So you can really see the difference in this. And let's bake that. Oops. Let's actually hit enter and not the period key. So we're baking that. And let's take a look at our results. So look at X. We said X was an amplitude of 1, a frequency of 1, and this is 8 octaves. And what you can see here is this fine jitter. Now we don't have as many points here, so there's a certain limit to where it doesn't make sense anymore to add more octaves. We could set a max on that. I'm not really sure what that is because I haven't tested, but because we only have so many points, and it also depends on your actual amplitude and whatnot, if your amplitude is really big. But you can see that there is a lot more micro variation on here. So that's how you get that really fine jitter. And if we look at Y, and let's look at these two over each other, you can see that Y amplitude is a lot greater, or I'm sorry, yeah, Y is a lot greater and half the frequency. So you can see the frequency is a lot less, but you get these micro jitters here. And then Z had more frequency and less amplitude. So you can see how Z is actually the smallest. So that's how we get our variation, and that's what the octaves is. It's the repeating it and getting those smaller variations. If you set it lower and lower, you'd have a much more consistent curve. Let's open this back up here. So that's what we do. We loop for every range. We generate, we call P noise, and P noise takes a value. And this is what we do here is and this is similar to when you're doing a sine curve to create, a curve like this. We send the time plus the seed times the frequency. So as the frequency is increased, the difference between these numbers, because time is going to be linear, because it goes 1, 2, 3, 4, 5 in the seconds. The seed is also constant, so pretty much this whole thing is just a linear rising number. And then we use a frequency to make the jump even bigger, which is what gives us those bigger differences. And then we take the result of P noise and we multiply it by the amplitude, which basically is what controls, actually this controls the frequency, and then this controls the amplitude. And that is what our value is, and we keep adding it. And that's how you do the fractal sum like that. So that's pretty much what getShake does. So you see that we send these values in, we get our new x, y, z, we set it out, and then we get our node. And close this here. Now, the way you get this really nice looking attribute editor output is, let me explain the companion files that go with creating a node. When you create a node, there are two more types of files that you can make. One is for the attribute editor, this AE shake node template mel. Now what that is it's actually a special naming. When you make a node, you have to create this mel script that's AE with a capitalization, the name of the node, and the name of our node is right here. And it needs to match up with the actual node. So what is in that, let's see here. Okay, what's in that is some basic mel, and again you can pretty much copy paste this, but this just basically tells the attribute editor how to lay out your options differently. If you didn't have it, there's a default that has some extra stuff on there that you may not want, like the caching setting and stuff like that. You don't have to write this, but if you, and actually I can show you what that looks like. Let me go ahead and okay, I'm going to comment out that here. So now we're not going to load. Let's close down Maya. And let's open up Maya again. All right. And let's load our plugin. I should have left it to auto load, but here we go. So let's load that. Let's create it. Now you see the difference. We don't have the nice fancy twirl down. We have all these default node values. So this could be perfectly fine. If we don't want to see these things though, then and we want to add our own sort of ways of representing these numbers, that's why we create the template. And what Maya will do is when it goes to create that node, it will look for, and actually I name this capital S. That doesn't really matter. It's actually the name of the proc. So it needs to match. See how it's a lowercase shake node, and I've got my name is shake node like that. So it will look for a matching template that's shake node template, takes the name of the node, and this is how it creates the template. And the other thing that we create to companion our node is this shake node command script, because there are some ways that this has to be set up, and I haven't explained where the time value comes from yet. You've only kind of seen it. But we create this convenience function, and what it does is it first checks if the plugin is loaded using commands plugin info. It asks if the shake node is loaded. If it's not, we generate an error. And then it creates the shake node for us, and then it connects. Now time 1 is a node that's always there, and its attribute out time is always spitting out the current time. So we connect time 1 out time to our shake node's time attribute that you saw that we set up right here. And actually more specifically where we set up right here. I could have said current time or time. And the last part of the command is we say that if the command if we passed in a transform node right here, then and it exists, well, we test if it doesn't exist, then it raises an error. But if it does exist, we help out by connecting the output of the shake node to the translate attribute on the incoming transform node, and then we return the shake node. So let's see what that actually looks like. Alright, let's make this a little smaller. Alright. So what we do is open a new shell here, and I'm going to do import shake node command. So now we've got our shake node command, and let's get the function. So we want to call create shake node. And this is the first way that we can run it. We can say, let's actually make this easier. Let's say from import shake node. Alright, now we've got this command, and we can just call it, and I'm going to say shake equals. So if I run it, now we get a new shake node. I can run this a couple times, and you can see new shake nodes. And so this is a convenience function that's already connected up to the time node, and we can actually test that out. Let's create just a random shape, right? And let's pass in the transform. So if you see, it's actually connected. So that's how this convenience function works. It's a lot easier than having to have this this whole set right here. So the idea is, again, to recap, you create your node, and then you create a companion set of functions that make it really easy to use it. And that's pretty much all there is to creating a basic node. And just to recap some more, you know, the example here of using this pnoise module is just a way of showing how you can, because of Python, you can go and grab existing libraries anywhere, you know, free off the internet, or, you know, shared resources that you've created before, and bring them into your definition of creating a node. And we've created this little hierarchy, and you know, it's a complete plugin. So that's it for this chapter on looking at the API. Okay, so this is a bonus chapter on how to install PyQt for Maya, and the benefits of that is, as we said before when we were doing the Qt Designer demo, is that there is actually a library where you can use Python completely to design your UI, and you get a lot more power, a lot more flexibility. But the reason that this is a bonus chapter is because it's a little more technically involved to install PyQt into Maya, because you have to build it. And so it takes a little bit more knowledge. But since the last chapter where I was talking about Qt, I was thinking, and I wanted to correct something that I had said when we were downloading the Qt version, and I said get 471 because you could build off of that later. You can't actually build off that, but it's good to have the right version to that matches what Maya is using. But I also was looking at an easier way to give you PyQt. And number one, if you're a Windows user, what you can do is, if you search for PyQt Maya 2012 precompiled, this first link you get, you can actually find people have built PyQt. You just, for Windows, this is really great because you can just download and install this, and so that sets you up for Windows. But I couldn't find anything like that for Mac. So what I did was I actually built an installer that I plan to include. I'll either include it in an installs directory like this if you're a Mac user, or at the very least I will include a links to where you can download this. And if you're a Linux user, I don't have a build for you, and I'm not sure if one is precompiled, but I assume if you're using Linux, you're somewhat savvy enough. And if you go to my blog, and I'll include a link to this as well at justinfx.com, I wrote up an instruction set on how to build PyQt for Maya. This was written for 2011, but since then I had updated it for 2012 with some just new versions. The instructions are the same, but with some new versions. But I will try to include this document with the tutorial, so that if you are comfortable compiling on a command line, you can actually build this yourself. But for Mac, I tried to actually put together something where it was pre-built, and there's one for Windows. So let's take a look at the difference. If we bring up our code, and I'll actually show you where it is here. It's in the PyQt directory under the asset importer. And before we had the Qt with the asset importer window and this UI file that we